Next, we're going to look at type 3 pH determinations. Now, recall from previous slides, previous lectures, that a type 1 pH determination involves determining the pH of an acetic acid solution in its buffering range, all right? A type 2 solution requires us to determine the pH at the equivalence point when the number of moles of sodium hydroxide is exactly equal to the number of moles of acetic acid originally present. Well, in this particular type 3 application, we're going to be looking at how to determine the pH of the solution when an excess of sodium hydroxide has been added. And in the words of this problem, we're asked to determine the pH of the solution after 60 milliliters of NaOH has been added. Now, the way to start a problem like this is much like we've started problems in the past, and that is to determine the number of moles of original CH3COOH, or acetic acid, that we have present originally, something that we have calculated previously, but we'll do again here. Taking the concentration of the original acetic acid and multiplying by its original volume, we determine that we have 0.0135 moles of acetic acid originally present. All right, now the number of moles of sodium hydroxide is something that we need to calculate also. Recall that for a type 2 problem-solving solution, we assumed that the number of moles of sodium hydroxide was equal to the number of moles of acetic acid present. That's the definition of what goes on at the equivalence point, but we are beyond that now. We actually need to know how many moles of sodium hydroxide have we added when we pour in 60 milliliters of sodium hydroxide. So to determine that number of moles, we'll use the concentration of the sodium hydroxide, which was 0.250 molar, given to us initially, and we'll multiply that by the 60 milliliters, or the 0.06 liters, to determine that what we have really added to the solution are 0.0150 moles of NaOH. Okay, so we haven't even considered neutralization yet. We're just looking at the number of moles of the initial acetic acid and the number of moles that we are dispensing into the solution as we add the 60 milliliters of NaOH. Now, we have gone past the equivalence point, which is to say that we have added more sodium hydroxide than what the acetic acid can actually neutralize. And so we need to know how much excess, how much too much sodium hydroxide have we added. That's a number very easy to determine because we realize that neutralization occurs between the acetic acid and the sodium hydroxide in a one-to-one fashion. So if we had 0.0150 moles of sodium hydroxide that we added, and we assume that all 0.01350 moles of acetic acid will be involved in this one-to-one neutralization, then only 0.0135 moles of sodium hydroxide can be neutralized, and what that leaves us with is an excess of sodium hydroxide of 0.00150 moles of sodium hydroxide that we added that went beyond what was required to reach the equivalence point. Now, it is these excess moles of sodium hydroxide that will now determine the pH of the solution. The equilibrium problems of past no longer present themselves here because the pH of the solution is going to be determined for our purposes entirely by the excess sodium hydroxide that's present. So it's very important that we determine the number of moles of excess sodium hydroxide, and now we can use this information to determine the pH of the solution quite simply. And here's how you do that. So the hydroxide ion concentration is what's going to determine the pH of the solution. And since the sodium hydroxide has a spectator, sodium, in a one-to-one ratio with the hydroxide ions, we also know now that the number of moles of hydroxide ions will be exactly the same as the excess moles of NaOH. All right, so we have 0.00150 moles of hydroxide ions floating around in solution, and then be careful, because in order to determine the concentration of hydroxide ions, you need to use the total volume, which will be the original 45 milliliters of acetic acid plus the 60 milliliters of sodium hydroxide that you've added, and here I've converted those to liters. When we do the arithmetic, we're able to determine that the concentration of hydroxides is 0.0142 molar. This concentration is the concentration that reflects the excess hydroxide ions that were put into this solution that were not neutralized by the acetic acid. We have gone past what the acetic acid can now actually neutralize, and this is an excess hydroxide ion concentration. But it's quite straightforward from this point. Now that we know what the hydroxide ion concentration is, we can go ahead and determine the pOH by taking the negative logarithm of the hydroxide ion concentrations, and we'll find that the pOH is 1.845. Very good. The question, though, was to determine the pH of the solution, and the pH always is 14 minus pOH, at least as long as the temperature is 25 Celsius, and we can do that subtraction and now determine that the pH is 12.154. So we've determined the pH of the solution. Where does that pH actually fall? Well, you can see it there on the graph. We have clearly gone past the equivalence point, and now we're looking at a very high pH, the result of excess hydroxide ions that have been added, unable to neutralize those hydroxide ions, and consequently we have now reached the third region of this titration curve where the pH, very high pH, is now determined mainly by the hydroxide ion concentration to be 12.154.